Go back now to the trajectory towards, if you like, a numerical example, some kind of path to a numerical example. We cannot do any numerics over here unless we start replacing this expectation into something that involves some form of summations, and therefore we need to sort of, go to and write this Bellman expectation equation for the state value function for v pi of s as follows. Okay, so let's try to see what will actually end up being as a formula. So we can actually do the derivation. You can actually skip this derivation. I am going to just do it for completion, for being complete here, but you can skip forward this kind of video if you are bored with this kind of derivation of the Bellman expectation. But I think it's worthwhile also following along. All right, so the first thing I want to do is to write the, so let me title this as derivation of the Bellman expectation equation for v pi of s. So I want to start with the formula we just saw, v pi of s, the state value of s under a policy pi, is this kind of expectation of the return gt, the average returns, in other words, that we will be getting from state s, given, in other words, st is equal to s. And this can be written as expectation. We will replace now the gt. Let me put a pi over here. We will replace the gt with the rt plus 1 plus gamma gt plus 1. And this return, we have actually seen that why this can be written like this as a function of the immediate reward and the next and the future returns for the future state that comes up after s, which is the s prime. So given st is equal to s, and therefore we can actually break it down into two parts: the expectation again of rt plus 1. That's the first part. I'm sorry, I forgot the conditional. Given st is equal to s plus gamma expectation over pi of gt plus 1 given st is equal to s. These are the two terms. So we will now take each of these terms and we are going to write them as follows. So the expectation, so the first term, let's call this first term A, and let's call this second term B. So A can be written as expectation of over pi. Well, we can replace the expectation, in other words. We can replace now the expectation with a summation. So we can write that for A, which is the expectation over pi of rt plus 1 given st is equal to s, is equal to a summation over all rewards that belong to the set of rewards R times, that's a definition of an expectation for that random variable. That random variable is the future reward. Okay, so it's an expectation over the set of rewards, all possible rewards. So it's R times the probability distribution of rewards. So the probability distribution of rewards is P of RT plus 1 is equal to R given ST is equal to S. I hope you agree that's the definition of an expectation operation. Okay, and we know that you can take actually this and write it as follows, is summation over R of R times, we can actually write this probability as another probability distribution that will involve as a marginalization of another more complicated probability distribution that will actually be the MDP dynamics, that will involve MDP dynamic, all the MDP dynamics. So we can actually write this as the probability, as a summation, over all S primes belong to the set of states S of P of RT plus 1 is equal to R, comma, ST plus 1 is equal to S prime, given ST is equal to S. In fact, we can actually even roll in here, not only just the S primes, the future states, but also the actions. So I can actually add here another summation and do the marginalization of the complete thing that I need. So, comma, A, T is equal to A, given ST is equal to S. All right, so from here to here, I hope it's understood, given, if you like, the sum rule of probability that we have seen in another video. By marginalizing this probability distribution, we are getting this. By eliminating effectively the random variables of actions and future states. And now what we can actually do here, we can write this term, and we can actually write this as another summation, again, over actions. So we can actually condition now to bring the MDP dynamics into the picture. So MDP dynamics needs S prime and R on one hand, and after the given symbol, we need to take the A after the given symbol, right? So we can actually do this, and we can write it as P of ST plus 1 is equal to S prime, comma, RT plus 1 is equal to R, given the things that we need, ST is equal to S, comma, AT is equal to A, times, let me write the times over here, the P of AT is equal to A, given ST is equal to S. Okay, so that's basically just a direct application of the product rule. So before we apply the sum rule to go from here to here via the marginalization, or equivalent from here to here, and over here we took the joint probability distribution and wrote it as a product of a conditional plus the marginal. Okay, so that is the product rule. So now we have all the elements that we need. By the way, this thing over here, by convention, notational convention if you like, we call this the pi of A given S. All right, so now we have the first term done. Okay, so the first term, this A, is done, and it involves the summations that we need, and for any numerical problem, we're able to just find a capital A term over there. Now, the next thing we need actually to do is to come up with the second term, right? Expression that involves summation with respect to the second term. In other words, replace this expectation again for the second term. All right, so now we have B. So we have here the by definition of the expectation operation, in other words, over gt plus 1 all over future return, the future return in the next time is gt plus 1, a random variable, times the probability of gt plus 1 is equal to gt plus 1 given, in fact, you know, since I was not using t indices for any of the specific values it will take, I'm just going to use g. Okay, so I'm just going to use g here. I'm going to eliminate the gt plus 1 here and the gt plus 1 there. So I'm just going to have, this is the sort of replacement. And now I need to apply a similar kind of thinking as earlier, and I'm going to write this probability distribution as resulting from a marginalization operation that involves for all four other summations which I had in my MDP dynamic probability distribution. So I need definitely I need my R, I need my actions, I need my S primes, and I have here my G's over here, and this is G, and this will be replaced now by gt plus 1 is equal to g, comma, st plus 1 is equal to s prime, comma, at is equal to a, comma, and rt plus 1 is equal to r, given, I forgot the given here, I forgot this conditional, so let me write it properly. It is p of gt plus 1 is equal to g, given st is equal to s. So I forgot, I now can do the given st is equal to s and close the parenthesis. And now I hope everyone kind of understands why we have, we actually can go from here after we marginalize all the other variables to here in this expression over there. Okay, this is effectively the sum rule. All right, so let's process that, and as you probably have guessed, I move the sum terms that I need on the other side. We take the summations again. The one is for R, S prime, A, G, and we had G over here, and now we will write this as gt plus 1 is equal to G, given st plus 1 is equal to s prime, at is equal to a, rt plus 1 is equal to r, and st is equal to s. Since we have taken this on the other side, then obviously we need to apply the product rule, and the product rule is the second is finished with the second term, st plus 1 is equal to s prime, comma, at is equal to a, rt plus 1 is equal to r, given st is equal to s. And now we will write this again as 1, 2, 3, 4 summations. And we can actually take the second term first, write it as we have done in the past with two terms that applying the product rule, that it will reveal the MDP dynamics of the first term, and of course the policy, that's a second term. And the first term over here, I think it's worthwhile commenting on the fact that the future rewards that we have here as gt plus 1, this probability distribution does not depend on many of the terms that are quoted here after the condition other than the state S prime. And this is because of the Markovian assumption of the MDP. We definitely do not have any dependency on future returns other than the state we are right now, the state that we are right now, the state that we have transitioned to, the S prime. Definitely we don't have any dependency on previous actions or even the current instantaneous reward that we have received. The only thing that we can give us the future returns in terms of this probability distribution is the ST+1 state. Now we are almost there because we actually can notice this term over here. And this term is by definition an expectation. But this time is an expectation over pi of, can actually write it as gt plus 1 given st plus 1 is equal to s prime, which by definition is the v pi of s prime. So actually can write this final expression as r s prime a. This is this is v pi of s prime times pi of a given s times p of st plus 1 is equal to s prime, rt plus 1 is equal to r, st is equal to s, and at is equal to a. And this is basically the conclusion as far as the sort of second b term of the v pi of s expression that we started with. And so we actually can see what we have done. So we have the expression v pi of s is equal to the first term. Well, but the first term was a summation over r that belong to a set of rewards times some summation over a summation over s prime. This was pi of a given s, pi of a given s times p, which is st plus 1 is equal to s prime, rt plus 1 is equal to r, given st is equal to s, comma, at is equal to a. That was our first term, plus we had gamma. Our second term, which the second term is this one that we actually see over here, which I'm not going to write again. So this second term is here. So gamma times the second term. And actually we can see here the common terms. We have pi of s and the transition, including all of the summations that are dependent on these s primes that we have here, and also the actions pi of s. So we actually can write it. So we can take this out, and what will remain finally, it is the following expression. So v pi of a is going to be equal to some summation over a of pi a given s times, let me see the final expression over here, so times summation of s prime belongs to s and summation of rewards of p, st plus 1 is equal to s prime, rt plus 1 is equal to r, given st is equal to s and at is equal to a, of r plus gamma v pi of s prime. So this is the pi of S. This is now a formula that we actually can reveal to us, can give us the path to a numerical kind of exam, numerical evaluation of the state of value, the value of a state S from the value of the state that follows, given the MDP dynamics that we know, and given a policy that we are going to be assuming, that probability distribution of a policy given that kind of a state, what kind of action we are going to be sampling out of it, and or what kind of action we are deterministically going to sort of follow every time we hit this kind of state. Okay, so this is the general kind of formula, and now we will see the numerical example.